This is Solar Rating and Certification Corporation specification sheet for a Heliodine Incorporated flat plate collector. It's a Colby 408001 collector. Just below this and to the right, here's a chart, thousands of BTUs per panel per day. Gives different weather conditions. That's the difference between the temperature of the fluid entering the module and the ambient temperature. So here at the top we have a -9 degrees difference, and then at the bottom we have 144 degrees difference positive. We see that on a clear day that's about 2,000 BTUs per foot squared per day. We have about 44,000 under this first condition, and down to 144 degrees difference, Fahrenheit difference, we have about 12,000 BTUs per panel per day. Over here on a cloudy day, it doesn't even give us anything for the 144 degree temperature difference. It does for a 90 degree temperature difference, and it's 4,000 BTUs per panel per day. We can find better information to use. Under the collector specifications, we see there's gross area, 32.23 feet squared. That's gross area. Gives the weight, gives the test pressure, gives us the aperture area, fluid capacity, collector materials, a frame, aluminum, cover, low iron tempered glass, the absorber, flat plate, the absorber coating, sputtered, selective, and so forth. There's better information shown here. If we want to calculate what the efficiency is at the flow rate of the test, then the equation, straight line equation, is, and remember, y is equal to mx plus b, so that here is the y-intercept, 0.736. Here's the slope, minus 0.741 BTUs per hour foot squared degree Fahrenheit. So we have to divide that by the solar radiation. And multiply it by the temperature difference. We see the flow rate during the test conditions, which is 0.79 gallons per minute. So let's look at some calculations here. Calculate the efficiency when the entering water temperature is 110 degrees Fahrenheit, the ambient temperature is 35 degrees Fahrenheit, and the solar radiation is 250 BTUs per hour foot squared degree Fahrenheit. Also calculate the stagnation temperature. That's the temperature at which the water in the collector would reach if the pump were turned off. So let's look at the first. Calculating the efficiency. We have the equation given, 0.736 minus 0.741 times the difference in the temperature of the water entering the collector and the ambient temperature divided by the solar radiation. So we insert the numbers. That's 110 degrees Fahrenheit minus 35 degrees Fahrenheit divided by 250 degrees Fahrenheit, and we come up with an efficiency of 51%. To look at the stagnation temperature, during the stagnation temperature, the efficiency is equal to 0. So, setting the efficiency equal to 0, doing a little bit of algebra, we have the water temperature is equal to 0.736, that's our y-intercept, multiplied by solar radiation, 250 BTUs per hour per foot squared degree Fahrenheit, divided by the 0.741 and its appropriate units, plus the 35 degrees Fahrenheit, gives us a stagnation temperature of 283 degrees Fahrenheit. Your homework assignment will incorporate these calculations You may want to refer back to these at that time.